Morning, ladies and gentlemen. Lecture 25. 1 month from now, we'll all be busy with Thanksgiving, and then shortly afterwards, it'll all come to an end. We have hopefully a powerful schedule before Thanksgiving. At the end of this month, 4 weeks from now, you will have some basic machine learning techniques that we haven't taught before to undergrads before, at this level, before this class. Today we'll start with Project 2 coming out this week. This is the standard weekly schedule. There's a homework due as usual this week. So project for this lab, Project 2, is the main lab, but there will be every lab, there will be a discussion worksheet on the topics that are being covered. So questions that you answer without using a computer. So there'll be that, and then you'll get going on the project. I hope you will enjoy the project. It's a very interesting set of data. Right. Courses that you might consider if you are interested in data science. I had a long post on Piazza where I basically said, look, we've been teaching this for decades. So there's a ton of stuff that you can already take. It doesn't have to have data science in the title. There are, however, 3 classes being new ones for next term. Stat 28 is already on the books. I told you a bit. I described the other 2. I do not have any more information. Please don't email me. What are the proposed dates and times? I don't know. I'd love to know because I'm supposed to teach one of them. Even if none of you takes it, I have to teach it. So the minute I know, I will tell you. And it is hard to be patient, and it is especially hard to plan your schedule around this. Don't plan your schedule around this. There's plenty of stuff that you can take. These will be offered, I think, unless something extraordinary happens in the future as well. How long do you have to be patient? Well, by the end of this month, which is coming up, right, next week, at the beginning of November, we should know about the formal approval of 2 of the courses that are still in the pipeline. And then it takes some time after that for courses to have course control numbers and appear on CalCentral. There's, steps that have to go through. Every time I have an update, I will post on Piazza. If I am not posting on Piazza, it's not that I have some secret information that you need to email me to find out. I just don't have any information. So it's really hard to keep writing back to lots of students saying, I don't know. I really don't know. I said I don't know. I still don't know. So I will tell you as soon as I know. Okay. We are now going to get to the business of quantifying what we have seen visually. And one of the things that we have noticed visually is that we've been trying to estimate numerical parameters. And there's a couple of things that have been going on. Our estimates sometimes are centered kind of around that numerical parameter, but they're a little bit spread out. The bigger our sample size, the narrower the intervals are. So there's this wide, narrow visualization that we've seen, but you'd like to be able to give it a number, because when you are doing a problem that is, you have some data that you're trying to analyze, there is a certain level of accuracy that you will want to have, right? Depending on the particular problem, that number will change, but there will be some level of accuracy that you want to achieve. For this, you have to know how big of a sample do I need to take to be able to achieve that accuracy with high probability. And so for that, you have to have some quantification of the stuff that we've been seeing visually. There's something else we've seen. We have sampled from horrible-looking distributions, and the empirical histogram of the sample mean has almost always come out to be bell-shaped. Sample proportions have come out to be bell-shaped, and it is a good idea to see what is going on there and whether there is some more powerful way of using that than we've had at the moment. So that's the business of this week. So I'm going to start with a measure that you're all familiar with. It's the average. We've used it, np.mean, np.average. I don't know why there are two methods that do the same thing, but there are. So I'm going to quickly list some basic properties that you can see from this very simple little list, 2, 3, 3, 9. The average is add up all the numbers and divide by however many there are. You get 4 1/4. I want you to look hard at the list, and I want you to look at that number and check that you agree with the following observations. The average is not necessarily a value in the collection. Yep? It might be, it might not. It isn't in this case. It doesn't have to be an integer, even if the data are all integers. Yep? Do not round, and you will see more why you should not round in just a moment, but notice that the average, unlike percentiles, is not necessarily a member of the collection. It's somewhere in between the min and the max. It's got to be somewhere in between 2 and 3, but it is not necessarily halfway in between. For this particular data set, 75% of the collection is below average. Yes? All right. It has the same units as the data. So if all the data were $2, $3, $3, and $9, then the average is $4.25. This one is worth understanding. The average is a smoothing or equalizing operation. And for this, I want you to imagine once again that those 4 values are $2, $3, $3, and $9. So you have 4 people, and that's how much money each one has in their pockets. What the average does, this portion, it says empty out your money and put it on the table. So this takes all, how much is that, $17? Yep. So it puts the entire 17 in a table, and then it splits it evenly 4 ways. So now each person has $4.25. And that equalizing function of the average is going to be a reason we're going to be using it as a what is called a smoother. All right, questions so far? Not meant to be very demanding, just it's useful to have all this stuff down in one place. So now I want to look at the calculation. The next slide is going to have the same list. Just remember that the average is 4.25. So your data are 2339. The average is 4.25, which is, we added the whole lot and divided by 4. That is the same by ordinary arithmetic as dividing each one by 4 and then adding up. You agree? Distribution of times and plus. Okay. So again, equalizing here. The first way of smoothing was to take everybody's money, put it on the table, and then divide that total equally among 4 people. This way is saying the person who has $2, divide your $2 equally. So how much do they get? 50 cents? Yes? Among 4 people? Then give the 50 cents to each person. Then the next person does it, and the next person does it, and the next person does it. This is equalizing one person at a time. It is very important that you understand algebra in this way, because there is something going on, that properties that you can use in the future. And so what you notice now is that by collecting terms, 3 appears 2 times, and so 3 is actually calculated 2/4, that is half of the time. And so the eventual calculation looks like that. Questions? And so what you should note is that the average is obtained by taking each distinct value. There are 3 distinct values here, 2, 3, and 9. Weighting, adding a weight, multiplying by a weight that is the proportion of times that element appears, and then adding up. So this thing you will have seen somewhere called a weighted average, but really every average is a weighted average. It's just sometimes the weights are all equal. Here, 3 has a higher weight than the other 2. And what this does is it allows us to see physically on the histogram where the average sits. And so I'm going to move to a demo. Questions about the arithmetic on here? Okay, so I have a ton of, yes. Weights and averages different. These are the weights, 0.25, 0.5, and 0.25. The weight of any element in your collection is the proportion of times it appears in the collection, right? You can use the weights and the distinct values to find an average. Yeah? All right. So I have a ton of tiny little data sets, and I'm going to draw you. Okay. That is a histogram of a list of numbers. What list of numbers? 2, 3, 3, 9. That is our favorite list of numbers today. Agreed? Okay. It is also the histogram of another list of numbers. 2, 2, 3, 3, 3, 3, 9, 9. What have I just done? So where I had a 2, I've got 2, 2. Where I had 3, 3, I have 3, 3, 3, 3. Where I had 9, I have 9, 9. Yes? So I've increased the size of the list. What have I done to the weights? Nothing. They're exactly the same. Yes? I've just increased each distinct value proportionately. Therefore, the average is still the same. The histogram is still the same. The proportions are still the same. It is very important to note that the calculation of the average doesn't depend on how many entries there are in the list. It depends on the proportion of each distinct kind. Right? So if I had a list where I had 200 2s, 400 3s, and 200 9s, it would have exactly the same mean, and it would have exactly the same histogram. So the average is a property of the histogram rather than of the detailed how many elements there are in the list. And so let's take a look. So any list that has a quarter 2s, half 3s, and a quarter 9s will have this histogram. And so now what I want you to do is, the reason I've drawn this thick gray line at the bottom is I want you to imagine that these are pieces of cardboard that you have attached to a wire. Okay? So it's a solid figure. And your game is this. You are going to run a pencil along here and see if it balances. So if I hold my pencil here, you see where my cursor is? That thing is not going to balance. It's going to tip over to the right. You agree? Yeah? If I hold my pencil here, it's not going to balance. It's going to tip over the other way. Somewhere in between, there is a balance point. Yes? Anybody who's been on a seesaw knows this. That balance point is the average. That 4.25 is where the histogram is going to balance. If you are interested in why that is, you will have to harken back to a physics class, which some of you may not have had, but for those of you who have had, just take the next few minutes to recall how you calculate a center of gravity. Principle of moments, anybody? Should I talk about this or not talk about this at all? Anybody interested? How many people interested? Okay. So, to find the center of gravity, you have to equate the moments on this side with the moments on this side. The moments are weight times distance. Yes, do you remember this? And the calculation for the center of gravity is weight times distance plus weight times distance plus weight times distance. That is what gives you the center of gravity, if you recall your physics. And so if you haven't had that physics, just, create the figure, take your pencil, and see where it balances. It's going to balance at the average. So what is the average in relation to the histogram? It is the balance point of the histogram, which does not necessarily have to be physically some kind of the center, because the histogram is not necessarily symmetric. All right? And so for symmetric histograms, which I hope is the next thing that I did, the game is very simple. So this is 2, 3, 3, 4. What I've done is I've taken the 9 and I've just slid it down to here, then the average and the median are both equal to 3. There is there's no doubt about what they ought to be. What happens is when you start to destroy the symmetry, the average can move. The average moves. The median need not. And so we are going to destroy the symmetry by, once again, moving this guy over to here. Okay, so I'd like you to take a look at this histogram. There appear to be 3 in here. There are actually only 2. There is the blue histogram that is 2, 3, 3, 4. And there is the gold histogram that is 2, 3, 3, 9. This kind of brown sludgy color is where the 2 overlap. Okay, so if you could just train your eye to see 2 histograms there and not 3, life will be a lot easier. Okay, so brown sludge and blue is our symmetric histogram that is centered right here at 3. The gold histogram is created by sliding this guy over. As you slide this guy over, the mean shifts. The mean moves to the right. That right-hand tail of your histogram, as you pull that 1/4, it takes the mean in its direction. The median remains unchanged because the median isn't affected by exactly where you're putting that extreme value. The median is affected by what's happening in the middle. All okay? Questions? So, a couple of observations. If you have a let's see. We saw that the average is the center of gravity of the histogram. If the distribution is symmetric, then that point of symmetry is both the average and the median. But if the histogram is skewed, it has a tail in one direction, then the average is pulled away from the median towards the tail. Right? Those tail, that is very large numbers, or if you have a left-hand tail, very small numbers, will drag the average away from the median towards them. And as an example of this, just to focus our ideas, I look at our salaries data. Okay, so that histogram, I think you will remember there's somebody out here. This histogram has a right-hand tail. The formal term is it is skewed to the right, but it's fine for you to say right-hand tail. Right-hand tail is actually very easy to remember. And so which one in this histogram do you expect to be larger, the mean or the median? I got both answers. The mean, okay, so wherever the median is, the average moves in which direction from that? Towards the tail. Right, the tail is on the right-hand side, therefore the average should be larger. That's what we expect. And if we do the calculation, median is 110, we've seen that before, and the mean is 114, so it is indeed larger. That is what you expect, and that's what you see. Income distributions often look like this. Lots of the people have low to middle incomes, and then there's a very few with very high incomes. And that is why when income distributions are summarized, people report median incomes rather than the mean, because the median picks up the more typical income. The mean is influenced by the Bill Gates and the Warren Buffetts and so on. So that's my spiel on the mean. Questions? Okay. So in some sense, it picks up the center of the data. It is not necessarily easy to see by eye where it's going to be unless you're really good at seeing where things are going to balance. But sometimes you can see whether it's going to be more this way or more to the left. You can see that. If the histogram is symmetric, then it's not ambiguous where the mean is going to be. Okay, so now the next thing is, of course, there's a mean somewhere. Where is the mean here? 100 and, so it's somewhere here. All of the values are not at the mean. There is a spread about the mean, and we're interested in variability of estimates, so we have to be able to quantify variability. So that's the next thing we're going to do, is to see how far off numbers can be from their mean. And okay, so my same favorite list of numbers, I think this weekend, I was just all 2, 3, 3, 9. Fine. If I'm going to find out how far off these numbers are from their mean, I better find the mean. And you know that that's 4.25 because we've been using the same list over and over again, boringly this time. And so now I need to find how far off the numbers are for them from their mean. Well, then I should do 2 minus 4.25, 3 minus 4.25, 3 minus 4.25, 9 minus 4.25. In other words, in array operations, I should take my array and I should subtract off the mean. So I've done that. And here you have the deviations from average. Yes, you have the numbers themselves and the deviations from average. So how far off a number is from the mean is called a deviation from the mean. Okay, now so what we want trying to do is get a rough idea of the size of those deviations. What I would like you to do in your head is try to take the average of those deviations. What's the first thing you have to do? You have to add them up. In your head, add them up. Minus 2.25 plus minus 1.25 plus minus 1.25 plus 4.75. What do you get? You get 0. That is not a feature of this list alone. It is a feature of every single list. Negative deviations correspond to values that are below average. Positive deviations correspond to values that are above average. The negative and positive deviations from average will exactly cancel each other out. It doesn't matter what the shape of the histogram is. Every single list. So if you're trying to get a sense of roughly how big these deviations are, then averaging the deviations is not going to give you a useful number because you're going to get 0 every single time. So then you investigate again what your question was. Your question was roughly how big are these deviations? We didn't talk about sign. We just want to know how big. Right? 2 classic ways of losing the sign. What are the 2 classic ways? Absolute value and square. Yep. Okay, so absolute value tends to have, it's an easier thing to understand, but it tends not to have such great properties because one of the things we're going to try to do, this is measuring variability. Often we are going to want to minimize variability for reasons that you understand. We're going to want accurate estimates. If you try to minimize things that have absolute values in them, those of you who have done a little bit of calculus will recognize that at some point you might have to try to differentiate something. Yep? The absolute value doesn't play well with differentiation. Function looks like that. Yep. What's bad about a function that looks like that? That corner. Corners don't work well. So we will set the absolute value aside, and we will take the next time-honored way of losing the sign, which is to square these numbers. So next move. Square these numbers, and I'm trying to avoid the cancellation. Oh, by the way, this was to remind me to do the following. If I do the mean of the deviations, I get 0.0. Okay, so we will square the deviations, and now you've got these, you've taken 2.25 and squared it, and 1.25 and squared it, and so on. You've got all of these numbers, squared deviations from average, and we'll take the average of these guys. And I get 7.68 something. Great. So I've got a sense of how big the squared deviations are, and in some sense that gives me a measure of variability, but it is very annoying because, once again, imagine that those values are $2, $3, $3, and $9. Then this is minus $2.25. Basically, you owe $2.25. Yep? So these are all dollars. What are the units here? Dollars squared. Yes? No sensible human understands squared dollars. So what you've done is you have got yourself into a good place by saying, okay, I've gotten rid of the signs, but you've caused yourself chaos by messing up your units. So now what do you think we're going to do? Take the square root at the end. And you get 2.77. That quantity, finally, that quantity is what is called the standard deviation of your data set. So my array was called any numbers. We went through a long process to find the standard deviation. I'll just summarize the process. This number is trying to measure roughly how far off the elements are, the data points are from their average. It is the root mean square of deviations from average, which sounds very complicated until you realize that it's just a recipe for what we did. These are the steps in order. Step 1, find the average. Agreed? That's what we did. Step 2, find the deviations from average. That's what we did. Yeah? Lose the signs, square the deviations. That's what we did. Take the mean of the squares. That is an interesting quantity. It's called the variance, and it does somehow measure variability, but it is messed up units. In the end, take the square root. Right? So if you just read that backwards, you have the method for calculating a standard deviation. So that is a formula. It's not in math notation, but it is a perfectly accurate formula. And I want you to notice, because of that SD at the end, because of the square root at the end, the SD has the same units as the data. So we're going to be saying things like, well, the data are around the average, give or take a few SDs. And it makes sense to add and subtract an SD and an average. Okay. So I'll pause. Questions? I'm just taking you through some technique. There was a question. Yes?
Instead of taking the square and then the square root, why can't we just take the absolute value?
Okay, so we went through the absolute value. The absolute value tends not to have good properties when you're trying to minimize variance. Right? The absolute value function is hard to minimize. It's just mathematically hard to minimize. Okay? So we're taking the square, but if you will hold for just a few more minutes, I'm going to give you today one reason, and on Wednesday, another reason why this is the measure to use, which goes beyond any technical mathematical issue. Okay? So just patience for a little while. More questions? So there is a natural question, why this? I mean, somebody else can be asking, well, I could have taken fourth powers and then taken the fourth root. Could I not? I could have done that. I didn't do it. So why this? So hold your horses. It's coming. Okay. So this is the sort of longest calculation I've shown you thus far. However, you have to believe that you can calculate a standard deviation. Yes. A lot faster. NumPy method for calculating the standard deviation. It's a NumPy method, therefore it operates on an array. Okay, so if you have a column of a table, please use dot column first to extract out the array and then use the method. You get the same answer. Okay. So now what I'd like to do, so what we have here is that the average of this list is 4.25 and the SD is 2.77. And what on earth does that mean? It is very difficult just by calculating the number to have any sense of what it does, and so the rest of the lecture is going to be spent seeing what this thing does. And for that, I'd like to take a data set. So these are not the same NBA players. These are from 2013. This is everybody in 2013, and we had their height, weight, and their age, well, in 2013. Height doesn't change. Weight maybe changes a little bit. Age certainly changes, and that's why it's age in 2013 there. And what I would like to do is take a look at this distribution of heights. These are basketball players, right? NBA basketball players. They're tall. Look at that horizontal axis. How tall are you? So here are the mean and the SD, 79 inches. The mean height of US men is 69 inches. They are on average 10 inches taller. And then there's an SD, which is 3.45. And what I'd like to do is I would like to try and understand what these numbers are measuring. And you recall that the purpose of the SD was to see roughly how far off the numbers are from their average. Now, what are the furthest from their average? Well, the tallest person and the shortest person. You agree? So let's look and see who they are and how tall and how short they were. Okay, Hashim Thabit, 87 inches tall, was the tallest person. And Isaiah Thomas, 5'9", great player, was one of the two shortest that year, right? So your data are centered at around 79. They're going up. The largest here was 87, and the smallest was 69. And what we're going to do is to see now start working like data scientists, which is we've got this scale here. This is in inches. What we are going to do is we're going to start at the mean and call that our origin. So the mean is 79 inches just right here. We're going to start here, call that our origin, and we're going to walk on either side in units of the SD. We're just going to see how many SDs away we are from the average. That was kind of the point of the SD. So for the tallest player, their height was 87 inches, and so to see the deviation from the mean, that's 7.9 inches above the mean. And what I want to know now is how many SDs is that? So there's 7.9 inches is the deviation, and SD is about 3.5 inches, okay? How do I figure out how many SDs is that? I just look at the deviation relative to the SD. And I want to be absolutely clear, because there are people looking at me going, yeah, go on, and there's other people going, I should understand what she's talking about, but, okay, it just isn't gelling. Okay, just pretend for now, forget the lots of decimal places. Suppose the SD is 3.5 inches. You all okay? Supposing there's a person who is 7 inches away from the mean. How many SDs away are they? The SD is 3.5 inches. They are 7 inches away from the mean. How many SDs away are they? 2. Yep. What did you do? You took the 7, you divided by 3.5. Yep. So you can do that with any SD and any distance. So to figure out how many SDs this is, I will take this deviation and I will divide by the SD. So Hashim Thabit was 2.3 SDs above average. Right? So if you start at the mean at 0 and you go right 1 SD, you go right another SD, and then you go another 0.3 SDs, you will hit Hashim Thabit's height. 2.3 SDs. Note the size of that number. That's not a lot of SDs. You agree? It's just a few SDs. And on the other side, Isaiah Thomas, notice the minus. Why minus? Because the deviation is negative. They're below average, yes? So this minus 2.9 says that this person was 2.9 SDs below average, right? Say 3 SDs below average. So what you're saying is that the very tallest was 2 and a bit SDs above average, and the very shortest was about 3 SDs below average. And so all of the people are within a few SDs of average. That's what you're noticing for this data set. So could you take the standard deviation from the median? It would be from the mean for the definition of the standard deviation is from the mean. There's something called the mean, the absolute deviation, which you can take from the median and then take absolute values. You don't get the computational power. But SD has one and only one definition. Okay, so for this data set, what you've seen is that everybody is within 2 or 3 SDs of the mean. So now there's the question of, is that true for all data sets and so on? So we'll try to answer that. One of the things I want you to observe is that this way of looking at data, let the average be your origin and then walk in units of SDs on either side. This is a classic data science way. It is called working in standard units. And we're often going to want to convert numbers to standard units. What does standard units mean? It just means how many SDs above average. That's all it means. Now notice that standard units can be negative They are negative SDs above average, means they're below average. So what I've done there is I've defined a function called standard units, which converts an array of numbers to standard units. It takes the number, it takes the array, it subtracts off from each element the mean, and then divides each one by the standard deviation. That's called a conversion to standard units, and I would like this to become like breathing for you, please. Right? So if I have a horizontal axis, how do I convert it to standard units? We've written this function. By the way, we are now writing lots of functions that we use over and over again. So you've seen bootstrap median, bootstrap mean. We keep using those functions. I'd like you to be able to write those functions. They're rather repetitive. This, for example, is a calculation that you write out. So these are not built into data science just because we feel that you can write them when you need them. In subsequent lectures, you'll see there's be a huge array of function definitions that I'll do in the beginning, all of which are functions we have written in class. Okay, so that function converts numbers to standard units. And the question that arises is for example, if I'm standing at the mean and I go 2 standard deviations on either side, right? So I walk 2 standard deviations below, I walk 2 standard deviations above, I pick up a bunch of the numbers, don't I? What percent do I pick up? It would be nice to be able to answer that. If I walk 3 standard deviations on either side, I'll pick up more. What percent is that? It would be nice to be able to answer that, and you know that you can't answer that. You can't answer that because that's got to depend on the shape of the histogram. Yep? So you can't say exactly what it's going to be. You can't even say approximately what it's going to be because histograms vary widely. But Chebychev, that name can be spelled in a variety of different ways, he created bounds that work for all distributions, no matter what their shape. So this is the first of 2 results that you will see this week that work for all distributions, no matter what their shape. And these results are powerful because you can use them in regards to populations that you don't understand very well. So this says for all distributions, no matter what their shape, if I stand at the average and walk plus or minus, I walk 2 SDs on either side, the percent that I will pick up is at least 3/4. If I walk 3 SDs on either side, no matter what the shape of the distribution, I will pick up at least about 89%. And the result is not just for 2 or 3, it's in general, if I walk Z SDs on either side, I will pick up at least 1 minus 1 over Z squared. And whether you understand that, whether you want to remember that last line or not, is not so much of an issue for data 8. But the first 2 you should remember. No matter what the shape of the distribution, at least 3/4 are within 2 SDs of average. Okay? This formalizes a statement that says, for all lists, the bulk of the data are within a few SDs of the average. Right? Students always want to know what a few means. That is how you make a few precise. Now, why is that true? You should ask your fellow students who are in Stat 88. They know all the gory details. But it's a beautiful result and very, very powerful, and it is the first reason for using the standard deviation rather than any other measure of spread. There is no other measure of spread for which there is such a beautiful and powerful result that cannot be improved. Chebychev's bounds are actually achieved for certain distributions. So you can't improve this without more assumptions on the variables. And so what I'm going to do now is I'm going to go to, actually, I'll pause for a second. Take that, absorb that, and ask me questions. Yes? Yeah, I haven't mentioned 68, 95, 99, so please wait. So as one thing to note, these, what I've written up here, at least 75%, at least 88.888, etc. percent, these are not exact values. These are not approximations. They are bounds, right? So what Chebychev is saying is that if you go 2 SDs on either side of the mean, you will pick up at least 75%. You may pick up 100%. But it's never going to be the case that you pick up 74%. So there's the difference between a bound, an exact value, and an approximation. You can't possibly get an exact value because you don't know the shape of the distribution. You can't even approximate because you don't know roughly the shape of the distribution. What you have is a bound. Yes? What's considered a distribution? Any shape of histogram. Any possible set of possible values with the proportions with which they appear. So every histogram that we've looked at is a distribution. Okay. So now I would like to go back to standard units. You remember how many SDs above average? I want you to note that these numbers, 2, 3, and in general Z, are standard units. These many SDs above average. And then minus 2 is that many SDs above average, so 2 SDs below average. Those are standard units. And so now I want you to imagine a list converted to standard units. We have our list of heights, and you've converted them all to standard units. Yep. So the heights list is in inches. Yep. So there's, well, we had 87 inches, 78 inches, 60-something inches, and so on. The standard units list is in what units? None. They're just numbers. It's how many SDs above average. So standard units are unit-free. That's why they're called standard. Okay, now imagine a standard units list. What kind of values are you going to see? Could they all be plus? Could all standard units be plus? Okay, so let's be clear about when do you get a plus standard unit? When the value is above average. Yes? Can all values be above average in a list? No, unless you're Garrison Keillor, Prairie Home Companion, where all his children were above average. But all the values cannot be above average. You'll have some plus and some minus. You might have some zero if you have some values that are at average. So in a standard units list, you are imagining a list of positive numbers, negative numbers, and some zeros. If you average those out, what are you going to get? 0. You're averaging essentially the deviations. You're going to get 0. And it's a fact that if you take the SD of that list, you'll get 1. So it's a list in standard units has mean 0 and SD 1. And now I want you to tell me how big, roughly. So if you saw something like 0.92 standard units, would you be surprised? 0.92 standard units means what's that value doing? I'm deliberately not writing this out because you need to be able to think about this. 0.92 standard units means that value is roughly 1 standard deviation above average. Yep? Is that a surprising value? Not really. So 0.92 is good. How about minus 2? Yeah, okay. Yeah, maybe 2 SDs below average. How about minus 7? Minus 7, you start to worry. Because that number is 7 SDs above average, and Chebychev is telling us something. Let's do an easy Z. How about Z equals 5? Right? So if I stand at the center and go 5 SDs on either side, then I will pick up at least 1 minus, what is it? 1 over 25. Yes? So 1 over 25 is how many percent? 1 over 25 is how many percent? 4%. Yes? And then 100 minus that is 96%. So between plus 5 and minus 5 standard units, you're picking up 96% of the data regardless of the distribution. So you should be very surprised to see minus 7 on your list of standard units. You should also be surprised to see plus 8.2. Right? It's not that they won't be there, but they're rare. And so now I want to look at some data. Actually, before I look at some data, questions about what's been said. I think it will become more concrete the minute we look at some data. Yes? Yeah. So the question is, if a number is 5 standard deviations away, maybe on either side, can I say that about 4% of the data, only 4% of the data is likely to be beyond that? You can say that at most 4% of the data is beyond that. Could be 0%, but no more than 4%. More questions? So let's take a look at a distribution with a very long tail and see what the standard units look like. And this is a distribution that should be familiar to you. It's our United Airlines flight delays, and what I've done is I've converted the delays to standard units, and I'd like to look at the code. So we defined a function which takes an array and returns that array converted to standard units. So we have our United table that we read in as we've done before, and then we augment it by a column, which is the function standard units applied to the array of delays. Just take a look at this line and make sure that you understand what has happened there. Table with column is just being used as it's always used. Table with column has the label of the new column, and then the array that is the values. This is the function standard units defined here, applying to this array here, and that array is these numbers. And we're converting these numbers to standard units. You want to take a look? Do those look reasonable as standard units? And the bulk of them are pretty small, right? And there's 1, 6, okay, so there's 1, 6, but we only see 10 of them. So how about we look at the extremes? And I am actually going to sort this thing. Look at that. 14 standard units, 14 SDs above average, 13 SDs above average. And on the one hand, as data scientists, we're going, whoa, that's a lot of SDs. And as people who travel, we're going, that's a lot of delay. Right? I mean, that's almost 10 hours. I don't know at what point they canceled the flight. I think we've had this discussion before. There was another data set that I had some poor person was 14 hours delayed. It was awful. Anyway, what you can see, vast, large standard units. Whereas Chebychev is saying, no, there aren't going to be that many of them. Well, we should check then, in case we have a mess up here. So what we're going to do is we are going to create a table called within 3 SDs, which is this table where the delay in standard units are between -3 and 3. Okay, those are all the delays that are within 3 SDs of the mean. Questions about that? That's what we're going to calculate, and then we're going to see what proportion of the data, what proportion of the table comes out that way. And look, it's 98%. Even for this very skewed distribution, 98% of the values are within 3 SDs of the mean. What does Chebychev say? Chebychev says that at least 88.888% are going to be in that range. This is 98, but it's fine. Okay. And I'm going to leave you with the shape of the histogram, and I want you to look hard at the horizontal axis. So these are the delays, and instead of minutes now, you have standard units. Starting next time, there's going to be a lot of standard units on the horizontal axis. Notice the origin is the original average. And you are walking 1 SD over 2 SD, that's 3 SDs above average, that's 3 SDs below average. You look at this data set, what we've just seen is that 98% is in this range. Yep. There's some stuff out here, you can't see it, but it adds up to about 2%. Right, I'll see you Wednesday.